I'd like to welcome the master students to the course Subject Matter for Teaching and to these videos that I'm producing as a means of supporting your learning in the sessions that I will be teaching. These videos will consist of pre-recorded videos that I have made from the PowerPoints that I've been using or from different aspects that I needed to record beforehand to deal with them in class, and some of the recordings of the session to build a coherent output for the session for you to refer to later. So these will also be up on YouTube, and you're welcome to subscribe to my channel as the Opinionated Science Educator. Let's begin by looking at learner prior knowledge. So what is learner prior knowledge? Okay, it is the information and educational context or beliefs developed from everyday experience a learner already has from previous learning, and this learning can include the experiences they gain from playing as young children about a topic. Now, learner prior knowledge therefore includes learner preconceptions and alternative conceptions about the topic being taught. So, what is the LPK for the particle theory, atomic structure, and chemical bonding? Okay. To begin this overview of learner prior knowledge, I thought it would be a good idea to look at what students learn about matter and materials from primary school and early high school. So, in grade 4, students do learn about the phases of substances. They learn that matter can be classified as solids, liquids, and gases, and they learn specific properties about solids, liquids, and gases, such as solids can't change their shape. Liquids flow, but they always stay in a container. You might also learn that it takes the shape of the container and so on. And that gases will not stay in a container, but spread upwards and sideways, or they take up all the space that is given to them. They also learn about phase changes. So they know that heating solids may change them from solids into the liquid state. They also learn that when you cool down hot liquids, you will change them into the solid state again, and they learn about the properties of the different phases. So at this level, okay, teachers probably only focus on the macroscopic properties of matter and also the macroscopic aspects of phase change. So they might learn that going from a solid to a liquid is called melting, from a liquid to a solid is called freezing, but the focus is only on the macroscopic aspects of matter. Okay, so at this level, they will not be taught about the particles that make up the matter, how those particles are arranged, and pretty much they would not have seen these different levels of representation brought together to explain what a solid is, how it differs to a liquid, and so on. And the same for phase change. Okay, they wouldn't have seen these levels of representation used together to help them understand phase change. Now, what do they learn in grade 6? Okay, in grade 6, they learn that some substances are soluble and other substances are insoluble. So they learn about mixtures, and here they learn specifically that, so here it's obviously only a solid and a liquid mixture, but that the solid can be seen in the liquid. Often the mixture can appear cloudy, and after a while the solid will settle out of the mixture. For solutions, they learn that the solid can no longer be seen. The solution has a glassy appearance. In other words, you can't distinguish it's uniform in how it looks, and the solid does not settle out. So again, they probably only see or have experience of macroscopic representation. So there's a glass of water with sand mixed in it. There it is in a jar, the water is still a bit cloudy from the tiny sand particles, but the larger sand particles have settled out and the organic material is floating at the top. And the same for solutions. They might have seen sugar being dissolved in water. They might even have been asked, what does it taste like? Do we know the sugar's still there, or the salt if they dissolve salt? They might have seen solutions where, for example, copper sulfate might be dissolved in water and they see that the color spreads out and the color is uniform in the solution. So we can know that they probably might have learned the difference between the solvent, the solute, and makes a solution, but they would not have seen a particulate diagram of this mixture. However, they are expected to know that matter is conserved when a solution is made. So the solids are still present in the solutions. The matter has broken down into small particles that aren't visible to the naked eye. So this is the only real indication, this idea of conservation of matter, where they are asked to think about the particulate nature of matter. Now, in grade 7, in the section Matter and Materials, they learn about the separating mixtures. So in other words, what a mixture is. They also are introduced to the periodic table of elements, how the elements are arranged, that some elements are metals, some are semi-metals, some are non-metals. So again, in terms of separation techniques, they're probably only exposed to seeing the separation techniques, maybe doing some practical work, but it's all at a macroscopic level. So they would not have been exposed to a diagram like this that is showing a mixture. How do I know that's a mixture? Well, the particles aren't joined. They're not chemically bonded. But at no stage have these students learned that a compound consists of a substance that can be broken down into simpler particles, and at the particulate level, that those are different atoms bonded together. So that's how I know that is a mixture. The particles are not joined together. And in the filtration, the residue stays behind and the filtrate would be the liquid. But students would not have seen these kind of submicroscopic representations when learning about mixtures. In terms of the introduction to the periodic table, probably the only representation they might have seen is the periodic table of elements. Maybe the teachers would have shown them what some metals look like at a macroscopic level and why they're metals, such as, well, obviously they will learn shiny, luster, and so on. Sulfur, which is a non-metal and a powder. Chlorine, which is a gas. But again, they wouldn't have seen, for example, a diagram like this, which is also an element. It's a diatomic element, but they would not have been introduced to the particles. So they wouldn't know, for example, that chlorine is a diatomic gas. What does that mean? That is only introduced in grade 8. There is a particulate representation of copper and silver. Why in this representation are the particles of copper smaller than the particles of silver? Obviously, it's based on the arrangement in the periodic table, but learners aren't introduced to the periodic table in terms of it being as elements cannot be broken down into simpler substances. The reason for that is that they're composed of one type of atom, because they've not been introduced to atoms at this stage. So, in grade 8, they are introduced to atoms as the building blocks of matter, that there are subatomic particles, protons and neutrons and electrons, that substances can be pure substances, some are elements, some are compounds, and that mixtures are not chemically bonded, they're not in fixed ratios. Often the definition for an element is that it's composed of one type of atom, which is a submicroscopic definition. And for compounds that is composed of two or more different atoms bonded together, again, that's a definition at a submicroscopic level. At a macroscopic level, we would say an element cannot be broken down into simpler substances, whereas compounds can be broken down into simpler substances. You must remember, up until this point, learners' experience with this section, matter and materials, has only been at a macroscopic level. And now in grade 8, we expect them to be able to define compounds and elements and have an understanding of these substances, often purely at a submicroscopic level, ignoring the macroscopic level, which is what they have the most experience with. Then they also learn about the particulate nature of matter, that all matter is made up of particles, that in a change of state, the arrangement of the particles change, that density is a measurement of the mass and volume, and at a particulate level, that the mass depends on what type of atom makes up the substance, or atoms if it's a compound, and the volume would obviously depend on the size of the particles. In terms, they also learn about the expansion and contraction of materials, that when materials are heated, the particles gain kinetic energy and expand. And then they also learn about pressure in terms of the particulate nature of matter, that it's the particles pushing against the side of a container, for example. Now, students then come with many misconceptions at this stage. For example, they all think that matter is continuous or has a continuous structure because they haven't really been introduced to the particulate nature of matter up until this point. Often they will think that the condensation of water on the outside of a glass is because that water has seeped or sweated through the walls of the container. Because they haven't, although they might know that air is there, they haven't learned that air consists of a mixture of particles which include water, and that water will condense because there's a change or difference in temperature. Then, when it comes to the expansion of matter, students think that it is the particles can increase in size rather than the spaces between the particles because of the increased movement. So they actually think the atoms get bigger or the particles get bigger. They also think that the particles of a solid do not move, and only the particles of a liquid and gas can move. As an extension to that, once they learn about the particulate nature, they don't think that there are gaps between the particles of a substance, or they think that these gaps are filled with air. So coming down to the misconceptions about the particulate nature of matter and chemical bonding have been researched thoroughly. So we know that when it comes to bonding, students can't differentiate between ionic and covalent bonding. They don't know the difference. There's no basis for understanding whether something is ionic or covalent. Then students have a poor understanding of the electrostatic nature of the chemical bond, and that it's actually an electrostatic force. Instead, they think it's something physical, like an actual thing rather than a force. Then there are misconceptions about the polarity of molecules, on the geometry of molecules. I'll get to that in the next slide. Then students confuse intra and intermolecular forces. Then they have misconceptions about melting and boiling points, or about solubility and electrical conductivity, or because they don't understand the polarity of substances and how that polarity is linked to the particles that make up the substance. And then this is where students would think that the atoms get bigger when a substance is heated, they sometimes attribute the macroscopic properties, such as expansion, to the particles. And so they mix the two levels of understanding, the macroscopic and the submicroscopic levels of understanding. They get them mixed up and confused. So this table, which was in one of the readings you were given, again highlights some of the common misconceptions. So for bond polarity, students often think that equal sharing of the electron pair occurs in all covalent bonds. For the shape of molecules, they think the shape of the molecule is only due to the repulsion between the bonding pairs of electrons. They don't take into consideration the lone pairs of electrons and how those lone pairs contribute to the shape of the molecule. And they only think that the shape of the molecule is due to the repulsion between the non-bonding electron pairs. So sometimes they confuse it and they think the shape is due to the non-bonding pairs. But they also think that bond polarity is what determines the shape of the molecule. And they don't consider the lone pair. So that is the common misconception related to how the electrons in a molecule contribute to the shape of the molecule. In terms of the polarity of molecules, they think that nonpolar molecules form when the atoms in the molecule have similar electronegativities. And therefore they don't, and that's because they don't consider the lone pairs and how that could contribute to making a molecule polar. In terms of intermolecular forces, they think intermolecular forces are the forces within a molecule. So again, you see they confuse intra and intermolecular. They think that strong intermolecular forces exist in a continuous covalent solid. Then the octet rule is often problematic. For example, many students think nitrogen atoms can share 5 electron pairs in bonding. 5 electron pairs, that's 10 electrons. That doesn't obey the octet rule now, does it? So these are the common misconceptions that develop, and probably they develop because students are not introduced to the idea of the particulate nature of matter early enough. So they don't think of matter as made of particles. They think of it as this continuous thing, and later it's more difficult to apply aspects related to the submicroscopic level to explain things like bond polarity, types of bonding, forces between particles. And so what we're going to do now is we're going to look at some of the topics or some of the sections that can be taught and how we can try address some of these misconceptions by ensuring that we look at the 3 different levels of representation in understanding chemical concepts. So that's what we will do once you have finished listening to this video. Are there any questions?
Yeah, Steve.
Yeah.
I've got just, for the 15 years that I've been teaching, the concept misconception, how do I explain this to teachers? I'm actually from the Department of Education and subject specialist. So when we talk strictly misconception, because when you ask this to teachers, they will tell you it's like misunderstanding of the concept.
Yeah, it's often they're called alternative conceptions. So it's an alternative conception, and it is in a sense a misunderstanding of the concept. But it relates to particular their thinking and their understanding. So in a sense, it's not incorrect to say it's a misunderstanding of the concept. So, for example, expansion. The misunderstanding is that the particles get bigger and not the spaces between them. So that's why it's a misconception.
Oh, okay.
Okay, anybody else? No questions?
When do we use bonds and forces? Are they not also creating a misconception as well?
Like I said, that's what Vanessa Kind argues, because all bonds, like an ionic bond, a covalent bond, a metallic bond, are due to electrostatic forces. All the intermolecular forces are electrostatic forces. The hydrogen bond is an example of an intermolecular force, but we call it the hydrogen bond. Van der Waal forces, which are much weaker, get called as Van der Waal forces, and then you get so yeah, that's why I say sometimes the language can contribute to misunderstanding. Okay, I want to end this part of the video by just re-emphasizing some of the things that came from the session, such as Tabang's question about asking teachers what misconceptions are. And yes, they often say it's just a misunderstanding of the concept. Now I realize it wasn't clear whether it meant through the teaching or ideas that they had before. But that's what misconceptions are, alternative conceptions that students bring that make it difficult to learn. I've seen with my work with looking at lesson plans from teachers, when you ask them about misconceptions for topics, they will say students' misunderstanding about chemical bonding, but they don't say what those misunderstandings could be. So teachers might be aware, yes, the students have misconceptions about this, but they don't know what they are. So yes, I'm on the Google page here to show you how easy it is to find out what those misconceptions are as teachers by just doing a Google search. So I'm typed in here misconceptions about spelling about the particle nature of matter. And I did a Google search, and I looked particularly for the resources, not the articles about the particle nature of matter. Because a teacher more likely is looking for a resource than wanting to wade through studies that report on student misconceptions. So as you can see, most of these are related to articles. Now, as a teacher should try and remain a scholar and find out what those misconceptions are. So yeah, that search didn't actually prove useful. So then I typed in common misconceptions because I want to know, or as a teacher, I would want to know, what do my students actually think about this? And this is what topic-specific PCK is all about, for teachers to start reasoning through and transforming their content knowledge. So they need to be aware of what the misconceptions are and how common they might be, because the teacher is doing the planning for their classroom in their context, and probably is not interested in what a study found about middle school students in the USA. They want to know what the common misconceptions are and how they could possibly solve them. So I think things like the best evidence science teaching, because they're resources for teachers that teachers can use. Okay, so this site is for UK teachers to help them teach specific topics. So it starts with what are the big ideas? Now, that's all part of PCK, making teachers aware what the big ideas are so they can start teaching towards big ideas to help students make the link. So, yeah, these resources are very helpful. And I chose this because I'm looking specifically for the misconceptions. So they've included here, what does the research say? They're telling teachers, these are the common misconceptions, and it's in the research, and this is what they are. So substances are continuous is a common misconception. Students don't think of it in a particulate idea. All the particles are located within a continuous substance. So the substance is continuous and it has particles embedded in it. So they don't think of the particles making up the substance, and then the particles are the substance. This is where they link macroscopic properties to the given to the particles, like thermal expansion. You heat a substance, the particles in the substance expand, not the particles move more, therefore they're create bigger spaces because they're moving more. They need to take up more space, and so the substance expands. They think the particles expand rather than the substance as a whole because of the movement and the need to take up more space because they have more kinetic energy, which results in the substance expanding. Okay, so those are some of the common misconceptions related to the particle nature of matter. As I said, they are research-based, and this resource is for teachers to get into, be aware of what the misconceptions are, rather than the teacher themselves wading through the literature, which teachers don't have the time to do. Okay, so just to show you that you can find student misconceptions quite easily by doing a Google search. I've now typed in student misconceptions about chemical bonding. And again, I don't want to look at the articles. I want to look at the teaching resources. So here's one from the Royal Society for Chemistry. So this page is about chemical misconceptions on chemical bonding. So it's a resource. It says this resource includes information about some key misconceptions. And it's in this book, which you can actually download, which teachers can download. Okay, so this resource then is about chemical bonding. It's a good resource for teachers to include because now it gives you what some of the student misconceptions are. So it says students see chemical bonding and forces as largely unrelated. And students then limit the category of chemical bonds to the types of interactions that can readily be conceptualized in terms of the full shell's explanatory principle. Okay, so as I said, it's good. There are resources to help the teacher about chemical bonding. So these resources are there, and this is what this course is all about. To develop your topic-specific PCK, you need to have knowledge of what the common alternative conceptions of students are, so that you can develop a teaching strategy to help deal with those misconceptions. So it's not about just knowing what the misconceptions are. It's about how you can use that knowledge to transform the content of teaching to help students understand the topic.